Ladies and gentlemen, in this section of the module, we're going to talk about finding hazard information. So for instance, if you're working in the laboratory and you have to use a specific substance or a chemical, where on earth do you find all of this information that you need in order to handle that chemical the proper way? Well, we've kind of already discussed some of it, right? So in the previous module section, we discussed this NFPA diamond. And this is kind of where I can find some of that information, right? So here's the diamond that you're seeing up at the top of your screen. And notice that we said the diamond is divided up into three other parts: a blue, a red, a yellow, and a white area. And if you closely look at the descriptions under each of these sections, for example, up at the top, the red is numbered 1 through 4. And we said the NFPA diamond was a little backward than the GHS. The NFPA diamond number 4 is the worst one possible. So if you look at the top, it says number 4 means extremely flammable under normal temperatures and pressures. Number 3 ignites under ambient temperature. Number 2 ignites with moderate heating. Number 1, it burns with preheating. And 0 basically means that it will not burn at all. Now keep in mind, this information is because the chemical is under fire. This is not the chemical sitting on the storage shelf just minding its own business. It has to be involved into a fire, which is why this is the NFPA diamond, right? And you can go through and you can pause this video if you need to and look at the health, the instability, and the special hazard codes that are assigned to each one of these smaller triangles. And this is what it would look like on the bottle, right? So here's the NFPA diamond, and we see a 2 for health hazard, a 2 for flammability, a 0 for reactivity, and basically no code in the white one at all. However, there is a statement that says it does cause cancer in laboratory animals. And down here at the bottom, it says for me to wear safety clothing, proper gloves, and an eye guard, as well as maybe a fume hood when I work with this particular chemical. All right. So the reason that I'm kind of reviewing this is because in this section, we are wanting to find hazard information. And that is one of the areas that we can find hazard information on a chemical or on a compound. But what if I need it before I go into the laboratory and before I get the actual bottle of chemical itself? There's certain ways and there's certain areas that I can get the information that I need to prepare myself from going into or before I go into the laboratory. So like always, I want to start off with an incident. And if we kind of carefully dissect the incident that happens here, a laboratory worker was preparing some samples using a procedure that involved isopropanol. If you're not really in tune with some of the chemistry terms here, that's okay. What I would like to do is kind of just review to you what isopropanol is, and this is nothing more than rubbing alcohol. That's all that it is. I can buy this into the Walmart. I can buy this in the grocery store. I can buy this anywhere that I want. Isopropanol is something that you have used over and over and over. So it seems to be safe. We use it every day, right? So when he finished, he poured the excess isopropanol into a plastic bottle that was labeled 2-propanol. For starters, isopropanol, prop means 3, 1, 2, 3. The iso unit basically means next to the last carbon, and then the ol, OL, is the OH group. So this is the structure of isopropanol, and that's also the structure of 2-propanol. Remember, we said that chemical compounds can go by different names. One of these is IUPAC, and one of these is a common name. Isopropanol is a common name that is used for that substance, and 2-propanol is the IUPAC name for that substance. So same stuff, no big deal. He did not pour it into the wrong bottle. That's the way that it was labeled. It is 2-propanol, and there we go. It says there was an immediate reaction, and the container burst and sprayed its contents on the laboratory worker. He was startled, but managed to call for help. So he's probably scratching his head at this point and say, what did I do? I did not do anything wrong. I poured this isopropanol into a container that said 2-propanol, and these two things are supposed to be identical. So when I poured this stuff into the proper container, why did this container burst on me? So that's why he was startled, but he at least managed to call for help. Nearby colleagues came to his aid, and when he reported that his skin was burning, they used an emergency eye wash and an emergency shower to wash away the splash. So here's another confusing bit of information. Skin was burning, right? And as you know, isopropanol, or rubbing alcohol, should not burn your skin. It burns open wounds, which is one of the reasons that we use it sometimes to sterilize things. But if you just put isopropyl or rubbing alcohol on your skin, it's not going to burn, or at least that it shouldn't. So this made them even more confused. There was a reaction that was going on with the exposure route, and that exposure route was dermal. It was on his skin, and it was beginning to burn. Isopropanol should not be doing this thing. He was taken to the University Medical Center for an evaluation and later released after being treated for an acid burn. An acid burn? It was just rubbing alcohol. That's all it was, or at least that's all that it should have been. Investigators learned that the bottle had been mislabeled and actually contained concentrated, that should be an ED, concentrated nitric acid and some copper waste. So here we have a reaction that took place, and that reaction was with rubbing alcohol, concentrated nitric, and a little bit of copper that was violent enough to explode a chemical container bottle. That bottle exploded, and it not only sprayed the rubbing alcohol everywhere, but it also sprayed the nitric acid everywhere as well. And all of this was due to a mislabel that happened in a laboratory. So as bad as I hate to say it, you can't trust other people in the laboratory. It almost is like a common theme that I keep talking about, right? But in this case, this person trusted someone else to label the container the proper way. Now, if the container was labeled the proper way, and that should have been 2-propanol in that bottle, the problem then was he trusted other people to put the proper chemical into that bottle, and they did not. So someone previously had nitric acid, and they decided to put nitric acid into the bottle that contained 2-propanol. This is where things start to fall apart, and this is where incidents begin to happen. Again, I've constantly said it over and over. Many times, it's not what you have done in the lab. It's what someone else has done in the lab prior to when you arrived, or prior to your shift, or prior to when you came into the laboratory to do what you needed to do for that day. So make sure that you are disposing of chemicals in the proper way. Make sure that you're using the proper containers, and make sure that you are not confusing what chemical goes where. Because if you do this, this incident can happen all over, and you can make someone else go to the hospital over a mistake that you have done in the laboratory. So what can we say about hazards, right? That's really what all this module is about. Hazards, and how to prepare myself for the hazard, and where I can find this information. Well, here's the scary part. Currently, if you look at CAS numbers, we've talked about CAS numbers already. You should know what those mean. If not, go back and review those videos. But if you review CAS numbers, there are now more than 90 million chemicals. Now, that doesn't mean that there's 90 million usable chemicals. That just simply means there are 90 million structures that have been identified. Maybe we've not used those. Maybe we don't know a lot about them, but they're out there, and they're a possibility. but there's 90 million of them. In addition to that, 1,500 are added daily. There's no way that you can keep up with all these people. There's no way. There's too many chemicals that are out there. They generate so quick that we cannot keep up with them. Doesn't matter who you are. It doesn't matter if you are just beginning your career in a laboratory. It doesn't matter if you're a laboratory manager that has had 40 years of experience. It's not going to happen. You can't keep up with all of the chemicals that are basically being added to the system on a daily basis. But again, most of them are structured. They're not usable. So I'm going to say in parentheses over here, most of them are phony. Yeah, phony chemicals, make believe. Sometimes that's where people like to reside, in make-believe land. Now, out of these 90 million, if most of them are phony, and they're just structures, and we've not really used them yet, how many of those 90 million are actually usable? Well, we're looking at around 80,000. Okay, so 90 million to 80,000, that is a drastic difference in the number. That's good news. Now I'll just have to worry about 80,000 chemicals. Well, again, doesn't matter who you are. You're not going to remember the safety procedures that are needed for 80,000 chemicals. If you do, you need to come and see me. Now, out of these 80,000, I'm going to say these are potentials to actually getting used. Out of these 80,000, less than 0.1% actually have hazard information. That's scary. Super scary. 80,000 chemicals, less than 0.1% actually have hazard information that I can find? And I'm sorry, I just now misspoke. It's not 0.1% of 80,000. It's 0.1% of the 90 million that have hazard information. So I just gave you a little bit of fake news, right? Okay, so 0.1% of the total CAS numbers have hazard information that I can actually look up and find. So out of these 80,000 that are potentials that I would see in a laboratory, yes, all of those traditionally have hazard information that I can find before I use them in the laboratory. And we're a little bit better than that because 0.1% of 90 million is around 90,000, right? So 90,000, so 10,000 more that maybe I would never see in a laboratory that currently does not have any kind of plausible use at all, period. I could at least have some hazard information if I wanted to look those up and begin to play around with them or begin to use them. But all of the 80,000 that are potentials, I've got hazard information that I can look up, that I can read, that I can study, that I can prepare myself before going into a laboratory. Now, as a student or as a entry level employee, you need to be concerned with the health effects. Now, it should be my job or an instructor's job to kind of warn you certain things about these chemicals, if they're pretty big ones, before you use them in the laboratory. And the same thing would go with your supervisor at work. If you are hired on with a company and they make you use a chemical that has some pretty serious health effects, then your supervisor, if they're doing the proper job, should basically be telling you, this is how you need to handle these chemicals. This is where you need to store these chemicals. This is how we make sure that nothing happens as far as our health, or as far as catching it on fire, or as far as blowing up the laboratory. So all of these health effects keep comfort knowing that someone, if you're entry level, should be kind of coaching you along about what to watch out for. But the sad part is that some instructors and some supervisors, they do not do this, right? So they're going to bring you into a laboratory and they are not going to tell you the things that you need to watch out for. And quite honestly, sometimes it's just due to the fact that they think that you should just automatically assume that you know what you're doing. Sometimes in their head, they think that some of the simple knowledge you should know. And that's not necessarily the case, because they could have been in it for 20 or 30 years. And maybe they know all of the dangers of something like an alcohol or an ether. And they just take it for granted that you know it as well. So where can we find this information? Well, this information can typically come from what we call the SDS. The SDS stands for Safety Data Sheet. And we've mentioned this before in the past, and now we're really going to focus on it. But the Safety Data Sheet is what we need to look up to find some of this information. Now, in the past, it was not called SDS. It was called MSDS, and the M stood for material. So it was a material safety data sheet. Now, we dropped the M. It has been renamed Safety Data Sheet, SDS, and that's it. These SDS sheets can be found in a laboratory. They can be what I would call hard copy, which is basically paper in a folder in a laboratory somewhere, or it can be electronic. Electronic copies are okay. They do not violate any rules or regulations. So if you do not have hard copies in the laboratory, if you've got a computer in the lab, that computer could have an electronic database, and that electronic database could have the SDS sheets that you would need as an employer. Finally, before I stop this video, you're probably wondering, if we go back to these numbers, 90 million plus chemicals, 80,000 of them are potentials. We are working on 10,000 more that we have health information for, or hazard information for. But why don't we have hazard information for all 90 million? And the answer is green. Where's the money, honey? Not all chemicals are tested simply due for money. If there is no plausible use for them, why do we need to know about them? If there isn't one laboratory in the world that uses that particular chemical at any point in time currently, why do we need hazard information on it? Right? And the reason is because if we start to do this, it requires testing. This testing, well, a company could sink in $50,000 to $100,000 just for the test that are required to prove the hazards that are associated with the compound. So if there is no commercial use, if there is no plausible use for this compound at this particular point in time, then why make the investment? There's no payoff. It's like loaning people money knowing that you will never get that money back. Why would you do that? Are you crazy? And if you keep doing it over and over, then you deserve to be broke. The same thing happens here. Why invest money into a chemical that right now has no use? It's not going to give you any money back, so ignore it. And then when a laboratory decides to maybe play around with that compound, or there is a use for that compound now, then we can make the investment to do some of the health studies and toxicity studies that are needed for someone to safely work with it in a laboratory environment. It's the nature of the game, right? It's all about money, because that's how the company makes profit. And if the companies do not make profit, you do not get a paycheck. That's how life works, people. So you can go out and you can say evil companies are making tons of profit. That is true. But they have to. Because they have to fork out funds like this that you don't get to see behind the curtain, not just your paychecks. All right, so in the next video, what we'll do is that we'll come around and we'll continue on with this discussion of safety data sheets and maybe where to find some of this health information that is pretty important in a laboratory.